Dear colleagues and friends, welcome to the 10th Conference on Quantum Foundations. It's been 10 years of quantum foundations in Argentina, 10 years of heated but friendly debate between colleagues from our region and all around the world. In the 10th editions of this conference series, we have gathered a selected list of keynote speakers that contributed to the development of this event in the past. We are grateful to them for helping us in promoting the research in the foundations of quantum theory in our region, a quite novel task indeed. There's also an extremely interesting list of contributed talks and posters. We are excited to hear that the interest in these research topics did nothing but grow during the last years. As is characteristic of this conference, we have gathered again a renowned list of physicists and philosophers from different countries and research career stages, trying to understand the foundations of quantum theory. 10 years ago, when we organized the first event of this series with Sebastián Fortín and Gustavo Martín Bosic, we had no idea about what we had ahead. But here we are celebrating, looking into the future years to come with the hope that the interest in the philosophical and foundational aspects of quantum theory will grow, especially among young researchers. The growing interest in this conference shows that it is not only the technical, but also the philosophical aspects of quantum theory that are essential for a better understanding of quantum phenomena. It is very important to acknowledge now the people who always supported these conferences from the very beginning, even when it was not so clear whether all of this was a good idea or not. We are speaking about Professors Olimpia Lombardi, Angel Plastino, Mariela Portesi, Walter Lamberti, and Anna Machtey, to whom we will always be grateful. We are also grateful to the agencies that made this conference possible on this occasion, but also in the past, namely the CONICET and the Agencia Nacional de Promoción Científica y Tecnológica from Argentina, the John Templeton Foundation, the CNRS, and the Laboratoire Sphere. We are also grateful to the journal Entropy for our partnership in publishing special issues associated with this conference. The call for contributions for the current special issue is now open, and it's not restricted to the speakers of the conference. You can find more information about it on the website. Before starting, let me tell you a short word on how this conference will work. In order to access the different presentations, you must use the Zoom links that you received by email. The conference will also be transmitted on YouTube. If you have any questions about the talks, please write them down in the Zoom chat so we can pick them up at the end of each talk. To all the speakers, we kindly ask you to try to stick to the time schedule tightly, since given that you all come from very different countries and therefore from very different time zones, it will be difficult to make all the talks fits otherwise. I'll stop stealing your time and let you enter directly into the conference. We're glad to have at the first speakers two Professors Karl Svozil from the Institute for Theoretical Physics of Austria and Gerardo Adeso from the University of Nottingham, United Kingdom. Please, Karl, feel free to share your screen and start with your presentation. Professor Svozil will speak about strong contextuality by non-faithful embeddability.
Thank you very much. I will now share my screen. And I would also very much like to thank you for this kind invitation. I can very warmly remember the time I spent in Argentina with all of you. It was a very good time, very productive time, and I hope these times will come back again when the international travel restrictions will be less severe and we'll be able to join in person, because personal interaction is very important in particular in the foundations of physics community, but in general, in physics in general, and in general human affairs. So let me just jump start on the topic. As Federico already announced, I will talk today about strong contextuality by non-faithful embeddability. And for those of you who are interested in the slides of the talk, they can find it here at this website. The only problem with the sign here, this is the tilde sign here, so please feel free or just contact me and I will send you the slide presentation. Now, let me give you some introduction, some general introduction to to the entire topic of quantum mechanics. Yeah, since I'm the first speaker, this might be pertinent. When we say quantum mechanics, since Dirac and von Neumann, we really talk about Hilbert spaces, which are vector spaces, that is ensembles or sets of vectors which are closed with respect to certain operations with a scalar product. And the scalar product serves as an interface to give you numbers, because you cannot measure a vector per se. You have no access to the vector, but you have access to, let's say, frequencies when you measure some observable with some probability or expectation, and there you need the inner product. And so all we are talking about are entities in Hilbert space. In particular, we are talking about vectors, unit vectors mostly. And then you have maximal observables, which in the sense of the spectral theorem can be understood as contexts. That is everything that can be maximally measured at once. Yeah, and those contexts are in a certain interpretation identified with orthonormal bases in those vector spaces. Whereas so this is quantum mechanics. Whereas in contradistinction, the classical entities are mostly based on Boolean algebras and on set theoretic operations within Boolean algebras, like set theoretic intersection, union, and so on, and so complement, and so on and so forth. So these are very different entities. Yeah. On the one hand, you have probabilities based on vector space entities, and on the other hand, you have probabilities, for instance, based on extreme events that you can then combine by convex combinations to give you the classical probabilities. And it comes as no surprise already from that perspective that you will get totally different predictions out of the vector entities as compared to the classical cases. And let me also say, this sounds a little bit, how should I say, general, but there is a metaphysical conjecture here, or one can call it a working hypothesis, that any measurement in a certain sense, which one can make a little bit more precise, and this is an ongoing debate for a century now, I believe, any measurement kind of creates or carves out a property, an emerging property that is, if with respect to certain side assumptions which are reasonable, such as non-contextuality, I will explain that probably to you in a second. No, not probably, but I will explain that to you in a second. There cannot be any pre-existent omnipresent properties of those objects relative to the assumptions. Non-contextuality means that the assumption that if you measure a particular observable within one maximal observable set, yeah, one orthonormal basis, you will measure the same value of this particular observable if you take another context. So let's say you have, let's say, an orthonormal basis in 3 dimensions, yeah, and you measure this observable here, and you rotate the context a little bit. So this value, the value of this observable, should remain the same, regardless of whether you rotate it or not. Yeah. So this is the meaning of non-contextuality, and it is very important here that I don't want to sound mystic, yeah, but in a sense you create the observable, yeah, by measuring it in a very precise mathematical sense, yeah, and this, I believe, will revise or make necessary a revision of our notion of the object in general. What is an object? What constitutes an object? Yeah. So see, since I'm the first speaker, I may give some visions, you know, and my vision is that in the long run, in view of quantum mechanics, we will have to revise our notion of what an object is. Yeah, and it will be more, how should I say, it will be more based on the properties we measure alongside it and how we measure it. Yeah, and how we view it. We probably create the object or some physical property in a very precise sense, quantum mechanically, rather than should think of a pre-existing thing. Yeah, and maybe it's quite simple to understand that, because in order to create that, you need not only what you call the particular object in question, but also the environment. Yeah, so you have a compound, an entangled compound between the object and the environment. This is the vision here, that creates the sensual impression of an object. Okay, so so this is my preamble thing, and let's get a little bit more to the to the formal facts of life here, facts of quantum mechanics. I will talk about contextuality here, and contextuality has many meanings, and one of the first people who envisioned that is Bohr and Heisenberg, and I have to accept that I wasn't very much aware of that until I read it more carefully, and until I read some papers, in particular by Krennikov and Jäger, and they pointed out that already Bohr and Heisenberg thought deeply about this idea that a physically observable may also depend on how you measure it. Yeah, but they had this not in an analytic way, but in a more synthetic way. Yeah, so they didn't do what we usually understand today as contextuality, but rather described it in metaphors and analogies and not in formal language. What nowadays is called contextuality consists basically of at least two cases. Yeah, the first case is you start with non-classical probability distributions such as the ones suggested by Gleason or Lovac. And you have on certain structures of observables, you have Cauchy type functional equations, and you ask yourself, what is the prediction with respect to those kind of probability distributions? Yeah. And then you try to construct something that is in contradiction to what classical probability theory tells you. So you try to find some probabilistic differences between quantized systems and classical systems. So basically, what you get there is you get Boole-Bell type inequalities that have been discussed by Bell and Froissart. Froissart is a researcher who is seldomly discussed in this context. Pitofsky, Cyrilson, Klauser-Horn, Shimoni-Holt, Suppes, Zanotti, and Capello, and so on. So this is the first type of contextuality, where you derive a probabilistic difference, the difference in probabilistic description in predictions, in probabilistic predictions of frequencies, let's say, for certain experiments in those contexts. And then you have the situation that you have gadget graphs. Gadget graphs means that you take some observables out of you take them from your quantum observables. Yeah, you take them from your quantum observables and take them and then try to interpret them classically. Yeah, also this is similar in spirit to the Bull-Bell type thing, but it's more directed. It's state dependent, and it says, well, I take and compound, let's say, a collection of observables that are intertwined, more or less tightly intertwined. But what is intertwined means, again, in 3D, you know, you intertwine two bases by just rotating, by keeping that kind of intertwining observable constant and just rotate it a little bit, you know. Then two bases, this one and these ones, are intertwining. They're intertwining in this common observable here. Yeah, and you do this a lot of times, and after a while, you come to a construction that is ingenious construction you invent or probably derived by graph theoretical computations or systematic searches of all graphs that has a certain classical property, because then once you get this structure of quantum observables, you try to force upon them a classical interpretation. Yeah, you say if say a starting point of my graph is, let's say, 1, then the end point of my graph, yeah, has to be 1 as well, has to be the value 1 as well. Yeah, so this is a state-dependent argument, and this is often called Hardy type. Hardy didn't invent that. That's a typical example of Stigler's law of eponymy, but it was actually Koch and Specker who utilized these, and many people followed them suit. So the idea is you got compounds of quantum observables that you force on which you force a classical interpretation, and you say you have some relational information. If this is true, then this must be true, or this must be false, and so on and so forth. Yeah. So and then you try to do the experiments and try to contradict the classical predictions. Yeah. And if the classical predictions, let's say, if you assume, well, if this is, you prepare a particle in that state and you measure it in another state, and you have in mind, you know, but this is an idealistic argument, you have in mind that all those intermediate, which are counterfactual observables, exist in your mind and also in reality. And if this has a classical interpretation, then the outcome must also always be that way. And you look at the outcome, so you prepare it, yeah, and then you measure it, yeah. And when the measurement is not according to your classical interpretation, then you say, oh, this has to be quantized because it is corroborated, of course not proven, but corroborated by the quantum predictions. And in all the cases we have seen so far, the quantum predictions have not been falsified, to speak with Popper, yeah, but the classical predictions have been falsified. So you assume that this is a good thing, and you call that contextuality, yeah. So these are two types that are based basically on probabilistic arguments, or on arguments that are directly related to a classical value definiteness. But then you have also a situation where you get something that is even more weird. you know, and Kocher and Specker already in their famous 67 paper had an example of that, and I will shortly, in a short time, I will show you this example. The idea there is that not only you get probabilistic differences between predictions, classical predictions and quantum predictions, and quantum mechanics is corroborated, but you get the structure of quantum observables that are beyond classical embeddability. Yeah, that is, you get two-valued states, more formally expressed. You get two-valued states that are insufficient to use them to generate a faithful classical embedding into a larger Boolean algebra. In the previous examples, there are many examples. Let's say the examples I mentioned with the true implies false and true implies true graphs or hypergraphs that still can be embedded in a larger Boolean algebra. But you get also graphs or hypergraphs which are totally, where it is totally impossible to embed them in a larger Boolean algebra and at the same time maintain the algebraic relations. So a homomorphic embedding, you cannot do that. Yeah, and the criterion is, the criterion of Kocher and Specker, I will show that in a second, is that the set of two-valued states is separating. That is, for any two atoms, you get at least two states where those atoms have different values. Yeah, and of course, you get a very strong form of contextuality, the strongest, possibly the strongest possible form of contextuality, where you don't have any kind of consistent with respect or relative to the assumptions you make, a consistent classical interpretation of these observables. That is, there is no way how you can associate falsehood and truth to those observables, because any attempt to do that results in a complete contradiction. You know, results in a complete contradiction. There doesn't, in mathematical terms, there is no two-valued state on such structures. Yeah, no classical two-valued state interpretable as classical truth assignment. So let me just summarize this again in what we actually do here from a tactical point of view. Yeah, you first take a suitable bag of observables that you take from somewhere. Let's assume you take them from quantum mechanics, but you can also take them from automaton logic, partition logic, or whatever. Yeah, but usually people are interested in quantum observables, so they take these observables from quantum mechanics. You take them in a bag, you know, and they are somehow connected, you know, intertwining. And then you interpret them classically, and you have your classical predictions, mostly in terms of convex combinations of extreme cases. And then you interpret them quantum mechanically and have your quantum probabilities, which are vector space based, yeah, based on vectors. And then, if you are lucky, there is a discrepancy between the classical and the quantum predictions, you know, and you realize, you quantize the system, you realize these observables, measure them one after another, and if there's a discrepancy, you can be quite sure that that quantum mechanics prevails, yeah, or at least is not ruled out. Let's say very cautiously with Karl Popper. There are three important issues here with these kind of arguments that one needs to keep in mind. The first is, which is a very interesting formal point of view. Once given such a bag of observables. And once given certain reasonable conditions on these observables, such that for every maximal observable, for every observable that are co-measurable, you need to have some classical probability theory on them. This is basically this additivity for co-measurable observables is probably the strongest condition you have. Then the question is, what kind of probabilities? I mean, in purely functional terms, what kind of probabilities can you do on them? You know, I will show you an example what I have in mind here. So this is the question. What kind of, given a bag of observables, what kind of probability is possible on these observables? You know, this may go beyond the quantum ones. Yeah, there may be weirder ones out there that may be realizable or thinkable, and maybe we find situations where we have this weirder kind of quantum behavior. But the intuition is really this classical quantum analogy. And then of course you may ask, well, if there is such arbitrariness, why are certain things so and not the other way? You know, and the answer to that is that one and the same structure of observers might have very different resources and very different realizations. And I came through that by studying automaton logic and generalized Uhn models that were invented by Wright, and compared them to to quantum observables. And for finite bags of observers, those are not very different, but they have when you realize them, they have very different probability distributions. So this is a very interesting, fascinating subject on its own. Let me give you some anecdotal example. Let's say this is usually called a pentagon or a pentagram, you know, depending on your preferences. The quantum logic community at first called them the house diagram. This was Kalmbach. Kalmbach called this the house diagram. Just consists of 5 cyclically interlinked, intertwining contexts, and you have a classical interpretation in terms of convex combinations of the 11. There are 11 two-valued states thereon, or I should say not two-valued states, 11 0-1 states thereon. Yeah, which means, what is a 0-1 state? Well, a 0-1 state is a state that associates, let's say, with one observable in every context a red, and all the other ones should be green. Yeah. So if I associate with A7 red, A6 and A5 should be green, and A8 and A9 should also be green. You know, because there can only be one red on each context. And this is a hypergraph that has been invented by Gricci and others. And then you might take this one, and then we are almost finished, because all that is left. Oh no, sorry. See, I did the wrong thing. That's good. Sometimes mistakes are very important. So this has to be green. This has to be green. And in order to make this consistent, the only way how you can color this is a red. Yeah. So these are. This is just one of the 11 two-valued states that are classically allowed. And in quantum probabilities, of course, these states are realized by vectors, and then you get a Born-type probabilities that have been discussed also, or re-derived with certain assumptions by Gleason and has also been in a totally different context developed by Lovac. And then you get another type of probability which associates. I don't have the color here, but let me show now. Let me show them with black. I have to erase that. No, I cannot. For some reason, yeah, here now. So I can make these and these and these and these and these. 1/2 probability 1/2, and these ones in the middle probability 0. Yeah, so this is the other exotic one, but maybe there exist more. We just don't know. Yeah, we just don't know. It's an interesting question on its own. Okay. So far, we are zooming in towards the end. So I will now. So far we have only spoken about different probability distributions on fixed collections of intertwining observables. Now we shall be talking about weird non-classical collections of intertwined observables. Yeah, and the first example that I found in the literature is already contained in this famous paper by Kochen and Specker, mainly famous due to this Kochen-Specker theorem that says there exist structures of quantum observables that don't allow any kind of classical interpretation relative to the assumptions made. But this one they discussed also, and this is very fascinating. They said that there exist structures of quantum observables that wouldn't allow a separation with classical means. What does it mean? Let me give you a preliminary gadget type of argument. If you assume that this here is true and this here is true, then you get a complete contradiction. Why? Because this has to be false here, this has to be false, and then the only way you can associate a value definite observable is here and here, but this is connected, and you shouldn't get in a single context. You must not get two true statements. Yeah, this is against the assumptions. So all you can do is, and I'm erasing these value assignments now. So all you can do is, if you assume that this is true, then this has to be false. Just because if I assume that if A is false, I get is true again. Also, I get a complete contradiction, as I argued before. So this has to be true also, and then this has to be true also. This is a meeting point. Yeah, same context. So you get two two false statements, and then you have another rule. There must be at least one true statement here. So this has to be true. So if you assume that this is true, this has to be true as well. And for symmetry reasons, you could also say that this and these observers cannot be distinguished by classical means. So you have a you cannot distinguish between at least two atoms. Yeah, or two pairs of atoms. In this case, you cannot distinguish between two pairs of atoms, namely this pair here and that pair here. And this is a typical case where their theorem, Kochen-Specker theorem 0 in this work is pertinent. It says that in order to allow classical embeddability, you need a distinguishability here among A and B here. Yeah. So now here you can, but let me see. Let me see. As I mean, here this A and this B should be associated with those observables here. Yeah. So you don't have that, and since you don't have that, you cannot embed them. And this is a much more stringent criterion than mere probabilistic differences. Yeah, these are structural algebraic differences beyond probability, and this is why I say, well, these are different examples. This is the original Cauchy-Specker type, and this is a new one in 4 dimensions, Hardy type things, and this is how I argue that in order to assure that a stronger form of contextuality emerges from non-embeddability in the sense of Cauchy and Specker, and there exist many graphs who realize that, and many also in 4 dimensions. I mean, I discussed this in a recent paper in 4 dimensions, how to generalize them to 4 dimensions. So there exist a lot of examples in quantum mechanics, which not only has this probabilistic contextuality, form of contextuality, and there exist even weirder forms of this type of contextuality, because, for instance, this graph that is based on a paper on a dissertation of the ETH in Zurich. Oh, there are two. Well, this is not good. It should be one pair of dots. This is based on a dissertation that was made under the guidance of Professor Specker. He gave it to me personally by Dr. Klabadecha-Seeberger, and she based her argument on a communication by Schütte in 1965. You know, Schütte gave a famous, an ingenious argument why certain tautologies that are classical tautologies cannot be quantum tautologies. And based on these configurations of observables, Dr. Klabadecha-Seeberger under supervision of Professor Specker in Zurich developed her dissertation. And based on this configuration, Josef Katlec in Prague proposed this bag of observables here. And this has a funny property that it is what is called non-unital set of two-valued states. So if you take all classical interpretations, you find out that the only classical interpretations that are allowed, that the only one must have this as true, and then those connected parts must be false. So all these observables here, no, sorry, they have to be true. Yeah, they have to be true because they are connected to the false observers. So they cannot be true. You know, so this is even more absurd, because if you prepare a state in a particle in that state, and you measure that observable, those observable never must happen according to classical predictions. But of course, according to the quantum predictions, and here is a concrete parameterization by Katlec, and according to those predictions, they occur. So you get a complete contradiction already here. And this is and one can prove that, of course, these are all non-classically discernible by classical means. So these are all non-separable, and you cannot create a larger Boolean algebra that embeds all of them. So this is even worse. This is even worse. And then there exist hypergraphs that I don't know if they have a quantum interpretation I strongly suspect that they have not, but they have interpretation in terms of generalized Uhn models of partition logics, which even weirder than that probability. So we are talking about structures of observables that may not occur in quantum mechanics, but in generalized Uhn models that have even weirder properties. That this is a structure that has been proposed by Grigi in 1971 already. He calls it G32, what I draw here is a realization in terms of partition logic, and this has the probability that it is not, that it cannot be colored, that the chromatic number of this hypergraph is 4. So you need 4 numbers, and this has some consequences on the classical realizability and on the realizability in terms of properties. So you need 4 basic properties in order to realize such a graph. This has been discussed in a recent work by Mohamed Sherakis and myself, and this points towards an even more weirder situation. So basically, what I want to say is, before I thank you for your attention, is that that contextuality has many meanings. Most of the time it is interpreted in terms of probabilistic probabilistic terms, but you can also interpret them in algebraic terms, and this is what I want to stress here. And after that statement, I thank you for your attention, and I'm finishing my talk now.
Thanks, Carl. Thanks for this very nice talk. And we have room for questions. So if someone has a question, you can put it on the chat. I have a question myself, and someone asked a question. Carl, you mentioned this sort of non-separability. And at the beginning, you said that there is a strong contextual behavior, that when you create a measurement context, somehow you have that the properties appear related to it. Well, in the literature, this has been related to non-locality, usually, so that quantum mechanics has an intrinsic sort of non-locality, and of course they relate this with the Bell inequalities. But of course there is always this tension between non-locality and contextuality. So some people will say, like I say, that somehow quantum mechanics is contextual and not non-local. But what's your take on that? What's your opinion? I would like to hear.
Well, I believe that at least as I presented it here, those are 2 different issues. You know, the one is you can have non-contextuality in a local and in a non-local configuration. Yeah. So if you for instance in the typical EPR configuration, you have an explosion view of those observables. Yeah. And you have relational information due to the entanglement of that state, but this is not necessary. And there are, let me put it a little bit pointedly, let me say, or controversially. Some people, and I don't want to say who, but one might imagine that some people say, why don't you need non-locality if this type of contextuality is already there? You know, you don't need that. On the other hand, I think from a physical point of view is one might say mind-boggling to see that behavior even among spatially distributed subsystems. you know. So from a pure, these are many times the mathematicians, they say, well, you don't need that, you know. But from a physical point of view, it's fascinating because space-time, you can say it's an a priori construct. I don't believe that, you know. I don't believe that. That's another issue. But it's still fascinating to see some different space-time points, and they behave in a contextual fashion. You know, they cannot be separated.
Yes, I see. And another question regarding just that theorem zero. Perhaps you know them, but we've been working with Decio Krause and Acacio Barros about how contextuality and indistinguishability are related. It's a sort of exploration, you know. We're still working on that. We have the thesis that somehow the fact that you have properties with the same content, but that can appear in the different context, that lies at the heart of it. So one possibility is that they become indistinguishable. Do you think that what you say here, just in this slide that you are showing, can be related to that?
Yeah, it may be. I think this is a typical example where we have to go over the argument, you know, and we have to explain to ourselves at some point. Yeah, I just be very humble. I say these criteria are out there for a long time. Have been already published in this famous article in these ingenious constructions by Koch and Specker, and they need to be taken more seriously. You know, they need to be taken more seriously because people are always looking at Koch and Specker's gamma 2. You know, the gamma 2 is this nice work that is in the Red Hat book, but they seldom look at the graph number 3. You know, this is well, I cannot because there is no time. I spoke with Specker about that often, and Specker was a little bit sad that not too many people listened also to the other works. So yes, the answer is yes, maybe, yeah.
Okay, thanks, Carl, for this very interesting talk. So now we have